Now we recall that Green's theorem says that the integral around a closed curve of p dx plus q dy is equal to the integral over the enclosed region with respect to area of qx minus py. Now we're going to mess with what we mean by p and what we mean by q. But if you remember, and remember that we proved this by just looking at the difference between this part of an integral around a small rectangular area and this part, and seeing how that was related to actually the change in the value of p with respect to y, and how the difference between this integral on this path and this path depends on how q changes with x. Okay, I'm not going to say any more about that, but that's why we have qx and py here, and you can review the details if you don't remember them. Okay, now, the thing you have to understand is that the p and q we're using here is not necessarily the same as the p and q that we're using here. Okay, in the application. But whatever's in front of the dx, we're going to take its negative y derivative. In this case it was p in front of dx. We're going to take the negative y derivative of p and put it into this area integral. Whatever is in front of dy, which in this case is q, we're going to take its x derivative. And then we're going to put those two together, and that's what we're going to integrate. The sum of the x derivative of whatever's in front of y and the negative of the y derivative of whatever's in front of x. And we did have extensive conversation about why this one is negative and this one is positive. Not going to allude to that right now, although I'm tempted. Okay, resist the temptation. Okay, so now we have again a function f equals pi plus qj. The gradient of f, and we know the gradient now. Well, yeah, I've written it out. Gradient operator partial with respect to xi plus partial with respect to yj dotted with pi plus qj is going to give us partial with respect to x of p plus partial with respect to y of q, which is px plus qy. Now this is a lot like qx minus py, except now it's px and a plus qy. You don't have a minus sign, and it's as I said, it's going to get a little confusing what corresponds to what, but we're going to use this idea in terms of what's in front of the dx, what's in front of the dy. Now, we want to do the integral of f dot dn, or the integral of f dot n ds. And I could write that. I think I have room to kind of write that small. Integral of f dot n ds. And the n ds is what we call our dn. And we're talking about a line integral around the boundary of a region again. Same situation as Green's theorem. So, our f dot dn is just, well, f is just pi plus qj, and that's dotted with what? That's dotted with the normal to our displacement increment along the curve, okay, along the boundary. Now, the displacement is ds, which equals dxi plus dyj. Okay? This is parallel, this is tangent to our curve at any point. dn has to be perpendicular to that, which means that it has to have, well, the dn vector has to have a slope that's the negative reciprocal of that of the ds vector. So how do we get a vector with a negative reciprocal slope? We switch the I and j components and make one of them negative. Now I chose to switch the components. We got dy now in front of I and dx in front of j. I have to make one of these negative. And I want this to be the outer normal. So if the curve is going like this and we're going clockwise around it, the normal vector should go outward from the curve, not inward along the curve. In order to make that happen, and I don't want to draw a lot of pictures, but think it through yourself, the dy is going to have to be positive, the dx is going to have to be negative. If you're going around a circle, okay, if you go from point here to a point here on the rim of a circle, your dy, well, I really can't wave my hands and explain that. And I'm actually losing my words trying to explain it without a picture, so I'm not going to explain it. This is what you've got. Okay. And here I say n dot dr has to be 0. Another reason we see that we can reverse our coordinates and make one of them negative. Clearly our n here, our dn here, is perpendicular to our ds here. We're going to get a dy dx minus dx dy. That's going to give us 0. So the normal's got to be either plus or minus dyi and a minus or plus dxj. If this is plus, this is minus, this is minus, this is plus. So I just explained sort of why it is we choose the plus on the dy and the negative on the dx. Okay. And I don't want to say too much more about that. That's what we do. Okay. Now, what then is our integral around the closed path of f dot dn? Well, pi dot dyi gives us p dy, and qj minus dxj gives us minus q dx. So our integral of f dot dn is the integral of p dy minus q dx. And that's going to be equal to the double integral of the coefficient of dy, x derivative thereof, minus the y derivative of the coefficient of dx. For the same reasons I said that here. Again, whatever's in front of dx, in this case it looks like p, in this case it looks like negative q, but whatever's in front of dx, we're going to take the negative of its y derivative. Okay, so that's this. The negative of the y derivative of whatever's in front of dx, and the x derivative of whatever's in front of dy, which in this case would be the p. So we end up with the double integral of px minus negative qy dA, which of course is just a double integral of px plus qy dA. And now we're going to say that this sum is what? Well, we just saw that up here. Okay, that's your del dot f. So that this is equal to the double integral of del dot f with respect to area. Now, what's this equal to? Ultimately, we started out with f dot dn. So the integral around the curve of f dot dn is the double integral over the region bounded by the curve of del dot f dA. Now we call this del dot f the divergence of f. And what I just said makes no sense. That's really kind of unfortunate. Maybe it does make sense. Never mind, it makes sense. Okay. I suddenly got my head into the realm of the curl, and thinking, wait, that's a normal component. It's normal, the curl of f dot dn is going to be equal to something else. Okay, so we'll talk about that in a minute. Okay, so this is valid. This is called the divergence of f, just as I said it. And this is the normal component of the divergence through the surface, through the boundary. This is in 2 dimensions. Now there's a 3-dimensional version of this, but this is well worth understanding before we get to that.